Okay. Okay, so hello everybody. It's a great pleasure to welcome today Pau Figueras from Queen Mary University in London, who will tell us about classical effective field theories of gravity in the era of gravitational waves. So please, Pau.
Well, thank you very much for the invitation. It's a great pleasure to be here. So shalom lekulam, ma shlomchem. And as Shahar said, today I'll be talking about this work that I've been doing in the past few years on classical effective field theories of gravity, and in particular how we can formulate them so that we can compute gravitational waveforms from first principles and get a better understanding of gravity. So, as you all know, we are in the era of gravitational wave astronomy. So gravitational waves are now being detected on a regular basis. And with the improvements in the current and future detectors, then we'll be detecting gravitational waves from various compact objects on a daily basis. And the precision of these detections will increase. And therefore, this will allow us to perform new tests of the strong field regime of gravity, namely the part of the in the case of a binary of a compact merger of compact objects, then in the merger phase, that's a strong field regime that we'll be testing. And these tests are going to become precision tests in the near future. So hopefully with that, one can learn about the fundamental nature of gravity. So with the current detections, we already know that, at least in these events that have been seen so far, that if there are any deviations from GR, those are small. So the fact that any deviations of GR small should sort of guide us towards what approach we take to perform such tests. And of course, in recent years, there's also been an increased interest in understanding classical effective field theories, namely how to formulate them. And relativistic viscous hydrodynamics is another area where there's been some significant progress in the past few years. So in this talk, I'll be just combining these various approaches to see how we can actually make these classical effective field theories predictive. So in the case of gravity, these issues in carrying out this program, namely testing GR with gravitational waves, is that at the moment, all tests assume GR. So the tests just check whether GR provides a reasonably good description of the measured gravitational waveforms, but we do not know whether some other alternative theory of gravity would provide a better fit to the data, because we do not have predictions from alternative theories of gravity. And one of the reasons why that's the case is because there is no preferred alternative theory of gravity. On theoretical grounds, there doesn't seem to be a preferred modification of Einstein's theory. And presumably all the available theories out there, which are in the hundreds, each one of them makes a different prediction. So we do not know what kind of smoking gun signal one should be looking for in the waveforms. And another related issue is that in many cases, we do not know how to extract the actual predictions from these proposed alternatives to general relativity. And mathematically, this boils down to the fact that we do not know whether some of these theories have a well-posed initial value problem. So since I'm going to be talking about well-posedness extensively in this talk, let me just get it out of the way. And just provide the sort of mathematical definition for you. So we say that some PDEs, in the case we should think of the sort of equations of motion of these alternative theories of gravity. So we say that they are well posed if there exists suitable initial data on a Cauchy surface, namely these initial data should solve the constraints and so on. And then we say that the initial value problem for those PDEs is well posed if there exists a unique solution of the equations of motion, and such a solution depends continuously on the initial data. So in mathematical terms, this means that the norm of the solution at some time can be bounded by the norm of the solution at the initial time. So this is important physically, because for example, when we do these numerical simulations, then in the initial data, these numerical simulations always have some error. So these numerical simulations will never be exactly on top of, or will have exactly the same physical parameters as sort of maybe, you know, the systems that we may measure on the sky. But these well-posedness statement, what guarantees is that the solution that we may, or the numerical solution will remain close to the true solution. So well-posedness gives us some bound on how fast the solution can grow in time. And this is crucial when you do numerical simulations. That's the only way in which you can hope to actually simulate the strong field regime of the theory.
How do you define a norm of a solution?
Sorry?
How do you define the norm of a solution?
It depends on, you have to choose a suitable Sobolev space, depending on, and that sort of boils down to the sort of number of derivatives that you control. For a second order PDE, then in the initial data, you control the up to the first derivatives, say, and well, so that's a difficult question to say. So in GR, you want to make, you want to allow for solutions which are as rough as possible. So you want to be able to control, because here we're talking about classical equations. So you want to be able to bound up to the second derivative of the solution. So that would be H2 typically. Yeah.
Okay, thanks.
So effective field theory is a framework that allows us to parameterize the effects, the deviations from GR in a systematic way, with and at the same time being agnostic about the UV of the theory. And this is why effective field theory is very powerful. And just to remind you, so at least at the classical level, to define an EFT, we need to sort of identify what are the low energy degrees of freedom. In the case of gravitational theories, this will be the metric, for instance. What are the symmetries that are realized at low energies? And then one have to come up with a power counting scheme so that we can then write an expansion and weight each term in the series. So in these gravitational theories, we'll just construct a derivative expansion. So this, where the zeroth order term or the first term will be the Einstein-Hilbert term, and then all the other terms will have higher derivatives of the metric, and they'll come with some dimensionful coefficient, which sets a length scale where new physics should appear. So we will demand that the derivatives of our classical solutions, the scale at which our classical solution changes, has to be much larger than this length scale associated to the new physics that we ignore. So of course, if you happen to know the UV complete theory, then you can take a suitable low energy limit, and then you can obtain these series expansions by this process of integrating out massive degrees of freedom. So in practical terms, so if you in say supersymmetric compactifications of string theory, if you take a suitable low energy limit, then you can get these gravitational theories with higher derivative terms. And in the case of supersymmetric compactifications, they start at Riemann to the fourth term with some precise numerical coefficient that tells you about the sort of properties of the compactification manifold, and it comes with a length scale, which is the string length. So, but you don't need to know this UV theory, but so you would write down the most general Lagrangian in this series expansion that is allowed by the symmetries. But you can also demand that the UV theory has some properties, for example, that it's unitary, that is Lorentz invariant. And imposing these constraints will allow you to sort of constrain the coefficients in this series expansion. And then you could then measure them in experiments and then determine whether those constraints are satisfied or not. And in practical terms, because in experiments we only have access to finite energy or certain distances, then one truncates the series because there are many terms in this series which one cannot possibly observe with, say, the precision that the experiment gives. So one consequence of working with these truncated effective field theories is that the resulting equations of motion are higher than second order. And this is a problem from a mathematical point of view. The reason is that for second order PDEs, we have a full classification of such equations, and we know when solutions exist. So for instance, for second order PDEs, they're classified in terms of elliptic, parabolic, and hyperbolic. but there is no such classification for higher than second order PDEs. So how do we even make sense of well-posedness for these higher than second order PDEs? And since these theories have more derivatives, one basically has to specify more initial data, which basically corresponds to specifying initial data for degrees of freedom, which are not present in DFT. And this is kind of a subtle issue that one needs to be careful with. So in the case of vacuum gravity, just as an example, and the simplest possible example, then the low energy light field is the metric, and symmetries are just diffeomorphism, say. And then with these two ingredients, then we can write down the most general Lagrangian. And this is what you would write down in derivatives of the metric. So the Einstein-Hilbert term is the leading order term, and then there are terms with 4 derivatives of the metric, then with 6 derivatives, and so on and so forth. And here I assume that there is only one UV scale L, but this need not be the case. And these are just numerical coefficients, which you would determine from either the UV theory or from experiments. Now, of course, one can perform also field redefinitions in a series expansion. And if you do such a field redefinition, then you can turn these terms with 4 derivatives to basically the Gauss-Bonnet term. And you know that in 4 dimensions, the Gauss-Bonnet term doesn't contribute to the equations of motion. So in 4 dimensions, without any further assumptions, then the leading order high derivative correction to Einstein-Hilbert would come at the 6th derivative level. And this would be a Riemann cube type term.
Question.
Yes.
So do you require that this theory will be well posed for
Yes.
all backgrounds, or is it for a well posedness for a specific background?
We want to stay to make this statement for all backgrounds, for generic backgrounds.
But then there's many indications that the only way that you can actually have well posedness in this case is with coefficients that are essentially too small to make any contribution. I'm sure that you know that very well.
Yeah. Let me continue.
That's why I gave you the opportunity to say that you're doing it on the background of black hole mergers.
Well, one could say, I will be discussing the cubic theory later on, and then maybe you can ask this question again. But I think that in this case, at least the kind of well-posedness statement that we make is general for any background. And I think that's also the case for the cubic theory. So there's no problem. I don't think you have to make any, well, let me explain how you make the cubic theory well-posed later on, and then I'll come back to your question about the fact that this coefficient has to be arbitrarily small.
I have a related question. Maybe
Sure.
maybe it's the same one. So when you're doing these field redefinitions and you're using the lower order equations of motion, you're
Yes.
already assuming that you have some hierarchy of equations of motion, right? That you have
Yes.
a lower order one.
Yes, that's
But
right.
then the higher order ones are perturbative, and then there's no issue with well-posedness.
I think it's one has to be careful with that, because you and I'll discuss this point shortly, but you cannot treat those terms perturbatively. At least, yeah, you cannot treat those terms perturbatively. I think you have to treat them non-linearly, but they have to remain small at all times in order for this truncation to be consistent in the first place.
Well, maybe linear. Non-perturbative. I meant that gamma or lambda are small. That's what I meant. Not
yes.
linear
No,
as in the
absolutely. I mean, in order for this to be consistent, they have to be small. Otherwise, you cannot meaningfully truncate the series at, say, the cubic order, right? If these terms, yes.
But do you mean perturbatively small or small? Perturbatively small, I mean that it's. If you're going to talk about this later, I'll just stop now.
Yeah, I will. I think this, what you're saying is a very good point. It's a subtle issue. What small means here. They have to be suitably small so that you, at all times, you have a hierarchy of scales between the various terms in the expansion. That's what you need. And those terms need to be at all times small. I'm not sure here what you exactly mean by perturbatively.
So let me say this. If I want to, at least the way I understand it, if I want to, let's say, solve the equations for the metric, I would say I expand the metric in a series expansion in L squared, and the leading term has to satisfy the usual Einstein equations, and the subleading term will be some sort of correction wherein I add the gamma or lambda or whatever.
Yes. So that's something which I will explain now. That's not going to work for these. That's not going to work. And you need to.
You're going to explain it?
Yes, I will try to. I will try to.
I'll wait.
You can ask me again.
Okay, thank you.
So then in this case, as I was saying, you get the equations of motion at fourth order. So what do you do? Now notice that in dimensions higher than 4, then the Gauss-Bonnet term does contribute to the equations of motion. So then in high dimensions, for those of us that at least part-time care about higher dimensions, then the leading order correction starts at 4 derivatives instead of 6. And because it's the Gauss-Bonnet term, then the equations of motion are second order. So one can use the usual PDE theory to study well-Poisson of this system. And this particular theory seems to be interesting to resolve certain singularities that arise. For example, I'm thinking of the Grigorov-Lam instability of black strings, but I will not talk more about this today. Okay, so also, people have a lot of interest in coupling the metric to some field, and the simplest one is a scalar field. So scalar tensor theories of gravity have become also very popular in the community. And if you do the same, if you apply the same reasoning for these sort of theories, then that's the expansion. That's the most general EFT with these 2 light fields that you can write down. And in this case, so that's the usual Einstein-Hilbert term, the kinetic term for the scalar with some potential. And then the other 2 terms are the higher derivative corrections. And in this case, they start again at the 4th derivative level. And so this is Hordensky kind of, this is a theory within the Hordensky class. So, So the equations of motion are second order. And Weinberg was the first one to write down this theory in the context of inflation, because so these new terms would capture the leading order higher derivative corrections to inflation. So the reason why this theory has become popular in the gravitational wave physics community is because the scalar equation of motion is sourced by the Gauss-Bonnet term. So if you have non-trivial curvatures in your spacetime, like in the case of black holes, then this theory is guaranteed to deviate from GR in the strong field regime. And people were very excited because presumably you could test it or even rule it out with gravitational wave observations. So from this discussion, then there are 2 types of higher derivative theories that naturally emerge. So ones are the ones I call special because they have second order equations of motion. These are these Lovelock or Hordensky class of theories that arise. And in this case, then one can use the usual theory of PDEs to study well-Poissonness. But then there are also the generic theories that in the case that you get, for example, in vacuum gravity in 4 dimensions, where you have higher than second order equations. So the question is, how do you set up the initial value problem for these theories? And of course, there's also a 3rd category here, which I call the Krapper theories, which are theories that are just crap, because maybe they do not have a well-posed initial value problem, or one cannot ask these questions meaningfully. We may agree or disagree on what kind of theories fall in this category, but probably we all agree that this class of theories is not empty. But anyway, so I'm not going to discuss them here. All right, so in terms of possible way forwards, there are the following paths that have been followed in the community. One is what Amos was suggesting. You linearize around GR. So this means that on a GR background, you compute the corrections to the metric induced by the new theory by the deviations from Einstein-Hilbert in a perturbative way. And if you do that, then there's no issues with well-Poissonness. Then because of course the corrections are governed by the linearization of the Einstein equations, which like wave equations. And while this approach is very flexible and it's been useful to sort of identify what are the sort of qualitative effects that the new terms could bring into the waveforms, the problem is that this approach suffers from secular effects. So it cannot be used to compute gravitational waves because you have this unphysical growth of the amplitude due to these secular effects. So one needs to really solve the theory non-linearly to avoid these secular effects. But again, what you do must be consistent with effective field theory. So the other alternative is that if you have a theory, you just find a well-posed formulation for it. And this may seem to be that is a lot of work because you have to do that for every different theory. But as I shall explain, then we've managed to find well-posed formulations for wide classes of reasonably, let's say, physically well-motivated and interesting theories, in particular, high derivative vacuum gravity and so on. And another approach that has also been applied successfully is to fix the theory following the Müller-Israel-Stewart to relativistic viscous hydrodynamics. And I'll also explain this approach. So in the rest of the talk, I will first discuss how to formulate the initial value problem for these four derivative scalar tensor theories of gravity and Lovelock gravities. Then I will explain how one can use this sort of Müller-Israel-Stewart formulation of relativistic viscous hydrodynamics in theory with higher than second order equations. And then finally, I'll present the more recent results on unified formulation for high derivative gravities, which includes the cubic theory. And I'll finally conclude. And I should have said earlier that if you have any questions, just stop me at any point. And you've already done that, so just keep doing it if there's anything that's not clear. All right, so let me first quickly discuss special high derivative theories. So these are the Hordensky and Lovelock theories, basically. And these were shown to be not well posed in harmonic gauge. And the reason for that is that in harmonic gauge, basically, one finds that all degrees of freedom, the physical, the gauge degrees of freedom, and the constraints, they all propagate at the speed of light. So these are degenerate. In this gauge, all the modes are degenerate. And in general, if you deform theory, which is degenerate, then it's no longer the case that you can diagonalize the sort of what's called the principal part. So when you try to establish well-posedness, what you do is you take a high frequency limit of your equations of motion and you look at the highest derivative terms, and then you diagonalize that system, and this tells you what are your propagating degrees of freedom and their speeds. And if your original theory is degenerate, it may still be diagonalizable, like in GR, but if you deform it in general, it will no longer be diagonalizable. So because the source of the problem is the degeneracy of the speeds of propagation in GR, in harmonic gauge, then the idea of Kovács and Real was to basically break this degeneracy. So by introducing some auxiliary metrics that control the propagation of the unphysical degrees of freedom. So in GR, to fix the gauge, basically one introduces a term here, which in GR, it's made of just a space-time metric, like the one in here, which fixes harmonic gauge. So the idea of Kovács and Real was to modify these gauge fixing term by introducing two auxiliary metrics. And the only property that these auxiliary metrics have to satisfy is that the corresponding light cones are nested with respect to the light cone of the space-time metric in this way. So the ordering doesn't matter. The only thing that matters is that these light cones do not intersect. So one of these auxiliary metrics controls the propagation of the gauge degrees of freedom, and the other one is the one that controls the propagation of the constraint violating modes. So if these modes are controlled by different metrics, they have different propagation speed. So the degeneracy is broken. And when you deform the theory by adding the Gauss-Bonnet term or the Hordensky-like terms, then the theory remains well posed as long as these modifications are small. And that's yes.
Pau, I have a question.
Sure.
It might be a repetition of Amos's question, but maybe in different words. You can hear me okay, right?
Yes, I can hear you fine.
Okay, so I understand that you're assuming that the curvatures are small compared to the scale of the corrections.
Yes.
And in fact, you don't know the full equations of motion. You know them only up to some order, or
Correct.
you don't know the full action. If you don't know the full action and the full equations of motion, you cannot expect to know the full solution. You can expect to know only the perturbative expansion of the
Yes, that's right.
solution. When you write the perturbative expansion of the solution, the equation is always second order, because
That's
at
right.
each order you separate, right?
Yes.
So the equation is always second order, and it appears that this issue of well-posedness doesn't appear. At each order, you have the linearized Einstein equation, the Lichnerovich operator, with some source, and the source comes from the lower orders.
Correct.
So then where is the issue of the additional derivatives? And I thought there was an issue maybe with extra initial conditions or data.
Yeah, not in this particular theory, because that's a Lovelock theory. It's always second order. So there is, in this case, there are no issues with
all higher order. My claim is for all higher order theories, for all higher derivative theories, there is no issue of additional initial conditions or a lack of well-posedness, because it is nothing but the solutions of the linearized Einstein equation at each order.
I agree with what you're saying, but the problem is that if you want to extract waveforms from these theories, then if you do it as you say, then one problem that one should address and has not been successfully addressed is the issue of secular growth of the perturbative solution that you would compute in the way that you indicated. And that this has been seen if you do exactly as you said, right? You solve the equations perturbatively with the corresponding sources. Then you see that the amplitudes grow, and this is an unphysical growth due to the secular effects. So if you want to, so one needs to address this issue. And
I don't understand this issue in depth. I understand the name. Does it happen at the first correction already? Is it a resonance effect, or is it?
It's not clear where it comes from, but this is something that has been studied in a certain amount of detail for the scalar tensor theories, where again you compute, you have, say, your background corresponding to a black hole binary. On top of this background, then you solve for the scalar equation of motion, and then you look for the corrections of the metric sourced by the scalar, right? And then in this case, then the modifications just have this suffer from this secular effect. So one needs
it reminds me of something. Maybe it's completely unrelated, but I will tell it very briefly, and you tell me if it could be relevant. When one discusses the anharmonic oscillator, just one-dimensional oscillator, and consider the anharmonic terms as a perturbation, then when you get to actually third order, then you find an equation which is unsolvable. You can sometimes call it secular. And then Poincaré suggested the way to do it by renormalization, we call it usually in high energy physics. We allow some of the parameters of the solution to depend on the small perturbation parameter. You know what I have in mind.
Yes. No, and
so in that case, that solves something that sounds like a secular problem. I don't know if a similar renormalization or dependence on epsilon would be able to do good here.
This has been tried. I can tell you this has been tried in some nonlinear equations, like model equations, but not in GR, or not in GR. So that's an open problem if you want to how to implement this renormalization group approach in gravitational theories. So this
so you cannot rule it out, at least.
No, and I think that this is something that should work along the lines that you mentioned, because that's basically what the problem is. However, the implementation seems to be highly non-trivial to the point that just solving the full theory in the way that I'm going to explain is probably more straightforward, at least at the practical level. But I think morally speaking, what you said is should work.
Good,
So-
good. Thank you.
Can I also comment on this one, or I don't know, just to make sure I understand? I mean, once you have these secular terms, then it just means that the perturbative expansion doesn't really see or needs higher order terms in order to really figure out what's going on. So the way I understand it, if I only have access to the perturbative expansion, it's not that the secular terms are, well, they're wrong in the sense that they bring you out of the expansion, but if the only thing I have access to is the perturbative expansion, then I just can't answer the problem of what happens when these terms grow. And for that, I need to somehow complete the theory. So you mentioned, but I have no guarantee. If I think of it as an effective field theory, I have no guarantee that thinking of these terms non-perturbatively is the right way of completing the theory. So,
yeah, absolutely. So these sort of ways to sort of handle these higher derivative theories I'm going to talk about, these are all, let's say, ad hoc UV completions of the theory. And these are, in a way, these are completely artificial for the reasons that you just pointed out, because you do not know what the UV theory. So because they are artificial in some sense, what you need to demand on the solutions that you compute is that they are not sensitive to this UV completion that you've put in by hand, right? Because that's something which, again, is, if you want, is a technical device that we come up with to sort of be able to sort of solve the theory non-linearly, but we ignore the UV physics, right? So you must ensure that whatever you compute is not dependent on how you've UV completed the theory. And that's something you need to do a posteriori, and you need to be very careful with, because otherwise you're not doing effective field theory. And we are treating these theories as effective field theories. So we need to make sure that's all the time.
Okay, thank you.
So I come back to my previous question or comment.
Yes.
It's highly unlikely that you will be able to do this procedure for several backgrounds. I give you the possibility of doing it, right? What you have is you're saying, okay, I'm going into the strong coupling regime of the theory, and now I want to do something to save me from that strong coupling regime. I would argue that if you go to the strong coupling regime, you're no longer well-posedness is already out. But I'm willing to give you the fact that for a specific background, as an effective field theory, if you can do this procedure that you described, then maybe it's okay.
Yeah, no, yeah. I mean, what I agree with you said. In fact, in these theories, the fact that you become strongly coupled manifests itself in different ways. So one of them is that, like this, what I was just talking here in this case, these well-posedness statements for this class of theories that the special theories only hold in the weakly coupled regime. And then you have absolutely no control, or at least a priori you do not know whether your initial data is such that upon evolution, the theory remains in the weakly coupled regime. And in fact, we know that inside black holes, even GR becomes strongly coupled if you want, and this series will only behave worse, right? So there's no guarantee that in a given background, then you will remain weakly coupled at all times, and that's something that you need to check. And it could be that in some cases you inevitably run into this strongly coupled regime, and then the theory is ill-posed and you cannot continue the evolution. But that's just signaling the fact that effective field theory is breaking down, and therefore you should not be using the theory beyond the weakly coupled regime. And that's something you need to monitor.
Okay.
So any other questions about this? Okay, so if not, I'll just continue. So what we did with my collaborators is just to extend this harmonic-like formulation to the other sort of coordinates that are popular in numerical GI, namely coordinates which avoid singularities. And just to show you that with this well-posed formulation, we can solve the theory, treating the corrections of Einstein's theory non-linearly. In this way, we avoid secular terms, secular effects, and we compute these waveforms from first principles. And at all times, we check that we remain in the regime of validity of effective field theory, namely that there is this hierarchy between the various terms in the expansion. And that's just for one particular choice of coupling. And this is just because I do numerical GI, I feel I have to show simulations. So this is just another simulation for a different kind of coupling. The only thing to note is in this case that the theory is basically GR until the merger, and then when the black holes merge, then an instability occurs, and then in this case, the black holes develop some scalar hair. So anyway, all right. And we can do the same in the case of Lovelock theories in 5 dimensions. So this is an ongoing work that I'm doing with my PhD student and Aaron Kovac. We solve for the Gregor-Laflamme instability of black strings, but now in Einstein Gauss-Bonnet. And there's some interesting physics happening as the strings approach the singularity, but that's for another talk. But this is just to show that we can solve this theory using this formulation. Okay, so now let me quickly review the work we did for the Müller-Israel-Stewart formulation, or inspired for general high derivative theories of gravity. So in this work, what we wanted to study is to formulate the initial value problem for an 8 derivative theory of gravity. So at the level of 8 derivatives, there are 3 possible terms that you can write down that cannot be removed with field redefinitions. And these are the terms that are written here. So since we're interested in developing the methods more than the actual making very precise predictions about waveforms, so we just ignore these other terms. One of the terms violates parity, I should say, but the other one does not. But we just kept only one term. And then if you derive the equations of motion, then you see that they are written here. And there are 2 terms with 4 derivatives of the metric, namely this term here and this other term over there. And then there are also lower derivative terms. So how do you...
Just to clarify, do you have 4 time derivatives here?
Yes, that's right. There are terms with 4 time derivatives. That's correct.
And you're not worried about ghosts?
Yes, one should be worried about ghosts. So in this way, we sort of handle ghosts. So that's basically what we do. So expanding on this question, then since we're interested in the leading order correction, and the equations of motion tells us that the Ricci tensor is order epsilon, namely epsilon is a small parameter, then the contributions of Ricci to the right-hand side are epsilon squared. So we only keep the terms that are not dependent on Ricci on the right-hand side. And that's basically just wild terms. And if you do that, then you simplify the right-hand side in this way, and you still get this term with 4 derivatives of the metric, and in particular, 4 time derivatives. So what do you do? So we want to find a well-posed formulation. It means that we need to reduce the order of this equation. In particular, we need to reduce the number of time derivatives to 2 time derivatives. And we want to do so in a way such that we can consistently incorporate these small corrections that the right-hand side adds to the solution, and do it in a way so that we avoid a strong flow of energy to the UV. So we do not want to, say, form or become strongly coupled outside black holes, right? Because then it will mean that the UV completion that we sort of, in this case, we build in by hand can let's say, have an impact on the physical predictions of the theory. And that's something that we do not want, because that's a completely artificial UV completion. And in this way, and we want to do it in a way so that we can study strong fields, say black holes, and at the same time remain in the regime of validity of effective field theory. So at all times, we need to check that the right-hand side of the Einstein equation is suitably small. So this is very similar to what happens in hydrodynamics. And let me just quickly discuss the Müller-Israel-Stewart formulation for a relativistic viscous conformal fluid. And I'm choosing a conformal fluid because it has more symmetries, so there are fewer terms in the expansion.
Sorry for
yes.
asking one more question.
Sure.
Isn't this procedure eventually equivalent to changing that theory that you started with to the Lovelock theory of the same order?
To the Lovelock theory. Not
Right,
sure if
you were right. The Lovelock theory is a theory at a given order that has two time derivatives
Yes.
and one more, right?
Yes.
So I'm wondering whether there is a difference between the theory that you get by just taking out the modes that corresponds to the ghost and the Lovelock theory of the same order.
At least I would say that this is different because, I mean, for dimensions, Lovelock theory does not has no dynamics. And here we are considering this in 4 dimensions.
Okay.
And yeah, so I think it's different.
Okay.
So yeah, any other questions? Okay. So in relativistic viscous hydrodynamics, again, one starts with a stress energy tensor for an ideal fluid, and then the viscous effects correspond to terms which have derivatives of the fluid variables. So at first order, there's the shear viscosity, which is multiplies the shear tensor, which is the symmetric traceless part of the first derivatives of the velocity field. And then you have higher order terms. In this case, these would be first derivatives, and all these other terms are second derivatives. So just as in the expansions that I wrote down earlier, then this would be the analogous to the Wilson coefficients that we had before. And if you happen to know the UV theory, then one can, in principle, compute those coefficients. And in the case of holographic fluids, then one can use holography to compute those transport coefficients. But otherwise, one determines them in experiment. And that's one of the things that, say, these heavy ion collisions do for QCD. So, but if you want to solve the fluid equations, then the fluid equations are just the conservation of the stress energy tensor, and they are third order PDEs in this case, because you have a derivative hitting this term, and this will give 3 derivatives. So how do you solve them? So Miller-Israel-Stewart came up with a way to solve this, which is consistent, at least in some instances, which is to basically promote all these higher derivative terms to a new dynamical object, which I call the viscous tensor, and then prescribe an evolution equation for this tensor. And the equation is chosen such that this object, which is, if you want, is a tool at this stage, such that this object evolves towards its physical value on a time scale, which is in this case given by this tau, which is a microscopic time scale. So this is a time scale which is much faster than any other macroscopic time scale in the system. And one hopes that by doing that, then, of course, in this case, now the resulting equations of motion just well posed in principle, at least in some regimes. And then one hopes that because this variable evolves on such a fast timescale, then it does not, it captures the right IR physics. But this is something that has to be checked on a case-by-case basis. So we do something similar here. So we started with these higher order equations of motion, and what we did is we promote this variable that had the highest derivatives, these higher than second derivatives. We promote it to a new dynamical variable, and we prescribed an equation of motion for this variable. And the equation of motion that we prescribe is such that this variable, this auxiliary variable, evolves towards its physical value on a time scale now set by the parameters in the equation that we prescribe. So because we do not know what the UV theory is, so we do not know what these parameters correspond to physically, so they're just a tool if you want. But what we need to do is, or we need to ensure in order for this procedure to be consistent, is that this time scale that is induced by these parameters should be much faster than any other physical time scale in the system. In this case, will be the light crossing time of the smallest black hole horizon. Whether you can always do that or not, this is something that we do not know, but at least for the case of a black hole binary, we could do that. Namely, we could choose this timescale to be much faster than any other timescale in the system. And furthermore, because what we are doing here is basically an artificial UV completion of the theory, as we were discussing earlier with Amos, then we need to ensure that the long distance physics is not sensitive to our choice of parameters. So that's something that we, when you do simulation, then it works for a certain choice of parameters, such that, again, this timescale, the associated timescales are fast enough. But then you need to do several other simulations to make sure that the waveforms that you compute are not sensitive to these choices of parameters. And as I said, this is something that a priori you do not know whether that's going to be possible or not. And the way in which we fix this theory is just the one I explained here, but actually we've been trying other approaches. And in principle, all of these are different UV completions, and one would like to ensure that they capture the same UV physics, the same IR physics. So that's something that remains to be studied. So just to give you an example, this is an example of a black hole binary in this 8-derivative theory of gravity. And what's shown here is this auxiliary variable. And on the scale of this plot, then you cannot distinguish this variable from the physical one, namely the Kretschmann in this case. That's because, again, we managed to be able to choose parameters such that the associated timescales are much faster than any physical timescale. So with this approach, then we can now compute these waveforms from different values of the couplings. I should say here that you see these massive shifts in the waveform depending on the sign of the couplings. That's because this coupling comes with dimensions, and the dimensions and the coupling that we chose is such that for a black hole, say 5 kilometers of a horizon of, say, 5 kilometers, then with this choice of coupling, then the UV length scale would be of the order of a kilometer. So this is like a huge coupling. So that's why you see this massive shift. But again, we were not interested in making accurate predictions from this theory. We just wanted to check that our procedure was consistent and it worked. And that's basically what these plots show. We can compute these long waveforms, nothing blows up, and it seems consistent and physical. And we check that throughout we remain in the regime of validity of effective field theory. And these waveforms are not sensitive to our choice of small parameters. Okay. So in the last remaining minutes, I want to introduce a new unified formulation of higher derivative gravities, which touches upon the question of ghosts that Rami asked before. So before I proceed, are there any questions any more questions? Oh, there's something in the chat. Okay. Sorry. Oops. Sorry about that. Sorry. Okay, so then I'll discuss the new formulation of higher derivative gravities. So for many PDEs, the issue of well-posedness depends on the highest derivative terms, and these are the so-called strongly hyperbolic PDEs. However, there are some other PDEs for which this statement depends on also some of the lower derivative terms, and these are the so-called weakly hyperbolic systems. And as I'll explain, these higher derivative gravities are weakly hyperbolic. So to illustrate this, I think it's useful to consider a toy problem, namely this model for a higher derivative wave equation in Minkowski space. So you have box squared equals to some source, which depends on the lower derivative terms. For the case of no source, then this is a linear equation. You can just take a Fourier transform, say in space, and then you can find all solutions. And then you see that solutions to this equation with 0 right-hand side generically grow linearly in time. So this polynomial growth in time is typical of weakly hyperbolic systems. But if you add this perturbation to the right-hand side, then again, you can find all solutions, and then you can see that solutions are of this form. And you can. Okay, can you? Is there any question? Sorry. So yeah, you can find the eigenvalues in this case, and then you find that at any time, then these eigenvalues blow up, which means that the solution is singular. So in this case, by just simply adding this lower derivative term, then you find that the system is no longer well-posed. On the other hand, if you add now this other perturbation, which is the usual wave equation, then you can find all solutions. And again, in this case, the solutions are just sums of massless and massive waves. And obviously, this problem is now posed. And in fact, more than that, for this kind of equation, then the behavior of solutions is much better than in the case with zero source, because now these are just sums of waves, so they do not grow polynomially in time. So in general, if you have a linear higher order equation of this form, such that the sources are just lower order wave equations and derivatives of those, then you can actually, by promoting these terms to new variables, then you can diagonalize, you can rewrite this original equation as a system of diagonal wave equations for these fields. And you can show that then these correspond to these extra massless and massive waves. So in this case, this is just a diagonal system of wave equations, which is obviously manifestly well-posed. And in our formulation of higher derivative gravities, the idea will be to rewrite the equation in a way such that you can get diagonal wave equations. So let's see how we do that. So in general, we consider a general higher derivative theory of gravity, and we consider just vacuum, just for simplicity, where these terms can be just polynomials of the curvature and covariant derivatives of these polynomials, and so on and so forth. So the leading order correction in 4 dimensions will be the cubic gravity, which there's a parity even and a parity odd term that you can write down. So we saw earlier that in effective field theory, you can make field redefinitions such that to simplify your expansion. Is that a question? Right. So here we do something else. We do a field redefinition, but now we add new terms to our action. And we make this field redefinition by adding this box to some power, up to some power n of the Ricci tensor, which is, again, the 0th order equation of motion. And such a field redefinition introduces to the Lagrangian then just these kind of terms, like wave operators, higher order wave operators acting on the Ricci tensor. And what we do is we add those terms so that we modify the higher derivative structure of the equations of motion. So if you make these field redefinitions, then you add new higher derivatives to the equation so that the resulting equation of the new theory is just this higher order wave equation acting on the Ricci tensor with some source term that has the same derivative structure as in the toy problem. So then what we do is, just as in the toy problem, we promote those other fields, curvatures, and wave operator acting on curvatures to new variables. Like, for example, in the case of the Weil tensor, we promote these to new variables. In the case of derivatives of the Ricci, we promote these to new variables. And then you can use the Bianchi identities and derivatives of those. And you can show that the resulting equations of motion are just a diagonal system of wave equations for these new fields. And of course, the original Einstein equation for the metric. And you can then show that these new fields correspond to massive fields, at least in Minkowski space. So all these curvatures that we promoted to new fields, Minkowski space, they correspond to massive fields, which some of them are scalars and some of them are tensors. But the point is that all their masses are of the order of the UV scale. So one would expect that for as long as you remain in the regime of validity of effective field theories, then you would not be exciting those fields. And if you do excite these fields, then then that would be a signal that you are not in the regime of effective field theory anymore. This approach, unlike the previous one that I discussed, this fixing of the equations approach, is fully covariant. It doesn't require any fine-tuning of the parameters. All you need to do is just to make sure that these masses of these new fields that you've introduced near Minkowski space are not tachyonic, but that you can always do. It doesn't require any fine-tuning. And in this case, since you have just wave equations, the system is just well-posed, regardless of the value of the coupling. Now, in certain backgrounds, if, say, you have backgrounds with black holes or backgrounds whose curvature scale is of the same order as the UV scale, then some of these modes are known to become unstable. And therefore, these instabilities, it's not that they are physical instabilities. I think they are just signaling the fact that your theory is becoming strongly coupled. So you can continue to evolve it, but you have exponentially growing modes, and if you do numerical simulations, your code is going to crash for sure. But this is just signaling. It's a way that this formulation has to indicate that you are no longer in the regime of validity of effective field theory. So you should not, say, trust the predictions that of this theory in this regime. So how large this and the number of derivatives that we are adding has to be. So this depends on the number of derivatives of the equations of motion of the original theory. So for instance, in the case of cubic gravity, the equations of motion have one derivative of Weil and two derivatives of Ricci. So our formulation applies with n equals 1, which means that you add to the action a term which is like Ricci box Ricci. And then you can formulate. Then the resulting formulation has just the number of fields you have is just the metric, two massive scalars and two massive tensors. In the case of quartic gravity, then the equations of motion have two derivatives of Weil and two derivatives of Ricci. And in this case, you need to add a term of the form Ricci box squared Ricci. And then the new degrees of freedom that you have are three scalars and three tensors. But I just want to point out that, for example, Einstein-Gauss-Bonnet in 4 dimensions, which is dynamical, has zero derivatives of the curvature tensors. And then you can formulate this theory using our approach by just adding these Ricci squared type terms to the action. And then you have one scalar and one tensor on top of the metric. So since I'm running out of time, let me just quickly summarize and conclude. So I've explained that we have different formulations that make these various theories, like Lovelock, Hordensky-like theories, and high derivative theories of gravity well posed. And these formulations can be used in, let's say, physically relevant settings of black hole binaries. And using these formulations, we can now compute from first principles the waveforms that these theories predict for these mergers. And hopefully one can then incorporate them to the, say, LIGO, Virgo pipelines to just test these theories. And there are many directions. This fixing method is very flexible, but it needs to be improved. In particular, the formulation I present is non-covariant. What we have not been careful with propagation of constraints, and so on and so forth. And it will be desirable to make further improvements because, after all, the Müller-Israel-Stewart formulation of viscous hydrodynamics has been very successful. We also want to test. We're now actually working on simulating black hole binaries in this cubic theory. So that's something which is ongoing work. So hopefully we can report on this soon. And this formulation in terms of extra degrees of freedom can be easily generalized to include matter fields. And these recent developments in hydrodynamics, these new formulations of viscous hydrodynamics by Noronha et al. And Kovtun can be understood in terms of these field redefinitions that I talked about here, and in fact can hopefully be generalized. So that's something which we're also thinking about. And with that, since I'm out of time, I'll finish. Thank you.
Thank you, Pau, for a very interesting talk. So we already had quite some questions, but we have some time for more. So please.
So I have a question, and I missed the first few minutes of your talk, so I apologize if I asked about something you said at the very beginning. But is there a distinct signal that you can see? Because at the end of the day, the parameters are very small. I mean, I would expect these corrections to be highly suppressed.
Yes. Yes. No, I think that this is a really good question, and I do not have a good answer to that yet. And that's basically what when we talk to the LIGO people and say, hey, now we can solve these theories. So here you have the waveforms. And they're actually, what they say is that what they really want is for us to identify what is a smoking gun feature in the waveforms that this theory predicts. And so for that, you do not need to have ridiculously small couplings, which is what the sort of physics tells us that it should be, right? If from theoretical considerations, you would think that these corrections are ridiculously small. So that's not what the LIGO people want. They want what features. They want us to identify what features in the waveforms could sort of say that, okay, this effect in the wave, this feature in the waveform correspond to this kind of modification. So that's something we are still looking at, and because that's the interesting thing. And to identify those features, one doesn't need to tune the couplings to be so small. So hopefully we can do that, but that's still work in progress. Now, that said, another effect. So another way that one could potentially see some deviations of GR is from the fact that these effects, even if they are very small, they may accumulate over sufficiently long periods of time, right? So for example, they promise us that for, say, stellar mass black hole binaries, some of them will be visible by LISA for a number of years, then they will go out of band, and they will be seen again at the merger stage in ground-based detectors. So one thing that we've seen so far is that because you basically have, in these theories, you have different ways, radiation works differently. So the theory radiates in a different way than GR. So you will see these sort of phase shifts with respect to GR. And this is like if you want, this is a non-local effect. So I think non-local effects are more promising in terms of observing or coming up with measurable deviations from GR. Because again, these are EFTs, right? So we treat them as EFTs. So it means that locally in space and time, your deviation from GR must be small. Otherwise, you're not in the EFT regime. So it's going to be very hard to identify local effects that are measurable. Have I answered your question?
Yes, thank you.
I have a suggestion for you about that. This is a typical problem also in BSM and so on. So the best way is concentrate on quantities that are known to be exactly zero in GR. And if you can find something that is exactly zero in GR and deviate from zero substantially in your theory, that would be a good thing to do.
Yeah, that's a very good point. So presumably, one such quantities I can think of is a love number. So in GR, black holes have zero love numbers. But I think in these theories, one can...
Yeah.
One
No,
could
in your theories, it will also be zero.
Yeah, so yeah, but that's a very good point. Thank you.
But for example, one thing that you can do, which is now very popular, is looking at the quasi-normal modes and
Yes,
their mixing.
absolutely.
And their mixing, and that could be something that might, because at that point the GR people are also looking at a small quantity,
Yes,
and so you can compete with them.
yes, but that's measuring quasi-normal modes is hard enough in GR, and I think the deviations, some deviations from the quasi-normal modes have been computed in these theories, and they're going to be ridiculously small. So, but yes.
But the point is, so for example, there are now some evidence that the mixing between some higher order quasi-normal modes and the lower order are of order of 10%. So if in your theory the mixing is zero, that
Yeah.
that's something that you can look at.
Thank you.
So, Pau, when you say radiation works differently in these theories, you mean there's like scalar radiation too, like other
Yeah,
modes
well,
of radiation, or
Yeah. Yes. Well, I
is
mean,
that
clearly,
the most outstanding way in which it differs from GR?
I think one should make these more precise. Let's say, of course, in the scalar tensor theories, you have another
Right.
degree, right? So then it's obvious you've got scalar radiation. But in these high derivative theories of gravity, basically all these extra modes I added, like the scalar, the massive tensors and massive scalar, these are like, I think, they're not physical, right? There's just a way in which we have to formulate the theory. But I mean, clearly, one needs to understand how, I mean, of course, once you sort of formulate the theory in this way, they will couple to the metric, right? So in some sense, then the metric will interact with those modes and and some energy will be carried by these modes. This is, if you want, at a practical level, a way in which this theory radiates differently than in GR, right? So that's basically what happens in these theories, and one needs to then try to quantify that and then see then how this impacts the mergers. Again, in the case of, one can fix the sign of these terms in the action, right, by requiring that the UV theory is unitary and all these things. So depending on the signs of that you have in the action of these various terms, you see that the waveforms move one way or the other, which is just a reflection of the fact that the theory is radiating differently than GR.
Okay, so it's not in these vacuum higher derivative theories, you don't have these new modes, but just the theory is different, so you'll have a different waveform. Yeah, okay.
Yes, absolutely.
What about the speed of propagation? Is it seen for all the modes in your theory?
Yeah. Well, these are massive modes, so they will propagate at speeds which are less than the speed of light.
No, I mean the gravitons.
Oh, the gravitons is C, yes.
Okay, and you don't have modes that propagate at nearly C, just
Yes, you would have some modes that propagate at nearly C as well, I believe. I'm not sure. Sorry, I take it back. At least in these theories where you have these massive modes, as long as you're in the EFT regime, then your sort of the energies that would go into these modes should be small enough so that these modes are basically massive. So they should propagate at a speed which is less than the speed of light. If these modes propagate at nearly the speed of light, then it means that you are exciting them with energies which are basically of the UV scale, and then I would be concerned that you're no longer in the EFT regime.
All right. Any more questions for Pau? If not, let's thank him again.
Thank you.
Thank you.
Thanks, Pau.
Thank you. Well, Yom Tov. Have a good day.